In this class, we'll try to learn about what are different lung volumes and different lung capacities. Different lung volumes are tidal volume, inspiratory reserve volume, expiratory reserve volume, and residual volume. Tidal volume is nothing but is the volume of gas inspired or expired during quiet breathing. So this is about 500 ml in adults. Inspiratory reserve volume is a volume of air inspired with maximal inspiratory effort in excess of the normal tidal inspiratory volume is called as inspiratory reserve volume, that is IRV. The normal IRV is 3.3 liters in men and 1.9 liters in women. Expiratory reserve volume is a volume of air that can be expired with a maximum expiratory effort after normal tidal expiration is called expiratory reserve volume, that is ERV. The normal ERV is 1.2 liter in men and zero point 0.7 liters in women. Residual volume is the volume of air left in the lungs at the end of maximal expiratory effort is residual volume, that is RV. The normal value of RV in men is 1.2 liters and in women it is 1.1 liter. So this is the diagram showing different lung volume capacities. So this is the tidal volume and this is inspiratory reserve volume from this point to this point. So this is inspiratory capacity, tidal volume plus inspiratory reserve volume, and this is expiratory capacity, that is the tidal volume plus expiratory reserve volume, and this is the vital capacity, that is it includes inspiratory capacity plus expiratory reserve volume, and this is a total lung capacity, so which is nothing but the combination of vital capacity and the residual volume. Lung capacities. Vital capacity. The maximum volume of air that can be expired after maximal inspiratory effort is called as vital capacity. And forced vital capacity, that is FVC, is the total volume of air that can be expired with greatest force and speed after maximal inspiration in FVC. The FVC differs very little from vital capacity in normal subject, but it is proportionately more reduced when there is airway obstruction with air trapping. The physiological importance of forced vital capacity. The maximum volume of air that can be exhaled after maximum inspiration is vital capacity. When expiration is performed as rapidly as forcibly as possible, the volume is forced vital capacity, that is FVC. Inspiratory capacity is the maximum volume of air that can be inspired after tidal expiration. This is the sum of tidal volume and inspiratory reserve volume. Normally it is about 3.5 liters. Functional residual capacity is the volume of air remaining in the lungs at the end of each tidal expiration. This is the sum of expiratory reserve volume and residual volume. Normally it is about 2.2 to 2.5 liters. It is important is that it helps in the maintenance of stable gas tension in the lung, so that at all times enough air is available for gas exchange along the alveolar capillary membrane. It prevents sudden alteration in gas tension due to any brief interruption in respiration. Total lung capacity. The volume of air present in the lungs at the end of maximal inspiration is the total lung capacity. The normal value in men is about 6 liters and in women it is about 4.2 liters. The lung volume and capacities are measured directly by simple spirometry. However, as lungs cannot be emptied completely following forced expiration, the residual volume and functional residual volume can't be measured directly by simple spirometry. RV and FRC are measured indirectly using dilution techniques involving helium dilution technique. Okay. So in helium dilution techniques, a technique in this procedure, the subject is connected to spirometer filled with 10% helium in oxygen, so which is called as helium oxygen mixture, and subject breathes from the spirometer. After the subject rebreathes helium oxygen mixture and equilibrates with the spirometer, the helium concentration in the lungs becomes same as spirometer. So applying the conservation of mass principle, we derive at the C1 and V1 is equal to C2 is equal to V1 plus V2, where C1 is the initial concentration of the helium in the spirometer, V1 is the initial volume of the helium oxygen mixture in the spirometer, C2 is the helium concentration after equilibrium, and V2 is unknown volume in the lungs. So thus unknown volume in the lungs is equals to V1 uh, into C1 minus C2 divided by C2. If the test begins at the end of normal tidal volume, end of the expiration, the volume of air remaining in the lungs represent functional residual capacity. If the test begins at the end of forced vital capacity, then the test will measure residual volume. Mechanical properties of lung and chest. In lung parenchyma, airways and pulmonary vasculature are embedded in elastic tissue. The inflation and deflation of the lung depends on their elastic properties. The physical principles that govern the process of breathing act mainly by affecting mechanical properties of the lungs. The lungs are elastic tissues, and elastic tissue, once stretched, recoils back to its unstretched position like spring. Similarly, lungs recoil when stretched. Ability of lungs to be inflated is called as stretchability or distensibility. Distensibility and elastic recoil are opposite to each other. Overstretching of the lungs causes loss of elastic recoil. Lung elasticity depends on the presence of amount of elastin and collagen fibers enmeshed in its parenchyma. Elastin fibers are highly distensible and can be stretched easily, but collagen fibers resist stretch and limit the lung expansion. The arrangement of elastin fiber works in the lung parenchyma is similar to the arrangement of fibers of a nylon stocking. When stocking is stretched to fit into the leg, the length of the individual fibers do not change much. However, the arrangement of nylon mesh in the stocking is such that it allows stocking to be easily stretched and fit into the legs. If the nylon stocking is overstretched, it loses its elasticity and becomes loose, that is baggy. Similarly, an overstretched lung, baggy lung, as seen in emphysema, can't be deflated easily due to the loss of its ability to recoil. Uh, Lung compliance. Compliance means the ability to stretch, that is, stretchability or ability to recoil. Lung compliance, that is, distensibility and elastic recoil of the lung, can be assessed from the pressure volume curve of the lung. So, this is similar to the inflation of a balloon, in which for each unit of change in pressure, balloon is distended to a new volume. Lung compliance, as I told, it's a measure of its distensibility. Compliance is represented by the volume change per unit pressure change. That is, compliance is equal to delta V divided by delta P, where delta V is the change in the volume and delta P is change in the pressure. Measurement. Two types of lung compliances are measured: static lung compliance and dynamic lung compliance. The static lung compliance, the lung compliance is assessed by analyzing the pressure volume relationship. So it is nothing but the pressure volume relationship is the graph obtained from human lungs by simultaneously measuring changes in lung volume and changes in the pleural pressure. For the recording pressure volume curve, the individual inspires maximally to the total lung capacity and then expires slowly. During the process of slow expiration, airflow is periodically interrupted so that alveolar pressure is becomes zero and the lung volume and the pleural pressures are measured. The lung volume is recorded as percentage of total lung capacity. The compliance, the volume change per unit change in pressure recorded in these conditions is called as static lung compliance, as air flow does not occur during recording. As the lung is deflated from TLC, the deflation pressure volume curve is obtained by this procedure. To obtain the inflation pressure volume curve, the lung is inflated from functional residual capacity to total lung capacity. Stages of this pressure volume curve. There are four stages in the inflation pressure volume curve. The stage 1, the stable lung volume, the initial change in the intrapleural pressure has no effect on lung volume. This is because decrease in the intrapleural pressure increases the transpulmonary pressure, and unless transpulmonary pressure is large enough to overcome collapsing effect of the surface tension created by the air-water interface in the airways, the decrease in the intrapleural pressure has no effect on lung volume. And stage 2 is the opening of the airways. When the intrapleural pressure decreases uh, above minus 8 centimeter of water, the lung volume increases, first due to the opening of the proximal airways and then opening of the distal airways. So this is the pressure volume curves while measuring the static lung volumes. Okay, so this is transpulmonary pressure and the lung volume change in percentage. Okay, so in stage 1 there is no change in the lung volume, and in stage 2, because of the opening of the airway, uh, the the amount of air which is going to enter into the lung is going to drastically increase. In stage 3, the linear increase in the lung volume when intrapleural pressure decreases further becomes more negative. Opening and expansion of all the airways occurs. This results in steep but linear increase in the lung volume. And stage 4 is suggestion of the uh, inflation uh, as increase in lung volume approaches TLC, further increase in the volume becomes less and finally it ceases. Okay. So here this is the stage 3 where again there is a steep increase in the curve, and in the stage 4 uh, it plateaus. The difference between inflation and deflation pressure volume is known as hysteresis loop. Okay. So here you can see, so this is the curve obtained during inflation and this is the curve obtained during deflation. Okay. And this loop is called as hysteresis loop. The hysteresis loop occurs because of the greater pressure difference is needed to open already closed airway than to keep the airway open that has already been opened. The slope of the pressure volume curve is the compliance and it is the measure of distensibility of the lung. The dynamic lung compliance measurement. Dynamic lung mechanics are the mechanics in play when the lungs are in motion. It is measured by continuously recording the change in the intrapleural pressure and lung volume. In the pressure volume loop of dynamic record, the rise in the volume in inspiration is in the form of a curve and returning to the starting point during inspiration in another curve. The dynamic lung compliance increases during exercise. However, dynamic compliance of the chest wall does not differ significantly from static compliance in normal conditions. Regional variation in the lung compliance. In upright posture, lung compliance is less at the top portion of the lungs than at the base. This regional difference in compliance is due to the effect of gravity. As discussed above, due to the gravitational effect, the pleural pressure is less, that is more negative, at apex than in the base of the lungs. At apex, transpulmonary pressure is therefore more, which causes alveoli in the apical region to be more distended. So this decreases the compliance of the lung at apex. Thus, the apex of the lung is less distensible. Thus, at the base of the lung, there is a larger change in the volume for the same pressure change, so which ensures greater expansibility. Factors that which affects the lung compliance: distensibility and elastic recoil. More the lung is distensible and elastic, more is the compliance. A stiff lung has a less compliance. Lung volume. The pressure volume curve of the lung is non-linear. which indicates that compliance is not equal at all the lung volumes. The compliance is high at low lung volumes and low at high lung volumes. Lung size. In general, compliance is proportionate to the size of the lung. Thus, the lung of rat has a less compliance than that of lung of elephant. Surface tension in the alveoli. Surface tension mainly affects the lung compliance. Surface tension at the air-water interface of the airways accounts for more than half the lung compliance. Clinical significance of lung compliance. The diseases that alter the lung compliance. Low compliance. The low compliance indicates less disensibility. So this means more work is required in a lung with low compliance to inflate the lungs to achieve the normal tidal volume. In restrictive lung diseases, the compliance of the lung is significantly low. For example, in pulmonary fibrosis, fibrous tissue is deposited in the lungs, which makes the lung stiff and difficult to inflate. In a normal lung, tidal volume 500 ml is achieved at about 2.5 centimeter of water of transpulmonary pressure. In lung fibrosis, the same change uh, in pressure produces a much less increase in lung volume. So this indicates that in this condition, static lung compliance is much less. So this is a static pressure volume curve in a normal and disease condition. In a normal, so this is normal. In fibrosis it is lowered, and in emphysema it is increased. High compliance is also equally bad as low compliance. High compliance is seen in obstructive lung disease like emphysema. Elastic properties of the chest wall. Like lungs, chest wall has elastic properties, but the elastic recoil of the chest wall is in outward direction. Thus, the chest wall has the intrinsic tendency to expand. The outward recoil of the chest wall balances the inward recoil of lungs. Therefore, if the elastic recoil of the chest wall is unopposed as occurs in lung collapse, the chest wall expands about 70% of the total lung capacity. That means when lung volume is less than 70% of the total lung capacity, the chest wall starts recoiling outward. So it should be noted that the outward elastic recoil of the chest wall is maximum at residual volume, and the inward elastic recoil of the lung is maximum at uh, TLC. So measurement of thoracic wall compliance. To measure the thoracic wall compliance, first the compliance of the thoracic cage and lungs are measured combinedly. Intrapulmonary pressure is measured for each lung volume inhaled. Then the lung compliance is measured separately. The thoracic wall compliance is then determined from the following formula. So 1 by thoracic wall compliance is equal to total compliance uh, minus 1 divided by lung compliance. So the thoracic wall compliance becomes lung compliance divided by total compliance into lung compliance minus 1. Lung chest wall interaction. During inspiration, lung and chest wall move simultaneously in opposite direction. The change in the volume of lungs and thoracic wall is equal as they move together. The pressure changes across the lung and chest wall during respiratory movement is called transmural pressure. The transmural pressures are transpulmonary pressure, transmural pressure across the chest wall, and pressure across the respiratory system. Transpulmonary pressure is the transmural pressure for lung. So this is the pressure difference between alveolar pressure and intrapleural pressure. To increase its volume, lung requires a positive transpulmonary pressure. When transpulmonary pressure is zero, the size of the lung is minimum. At zero transpulmonary pressure, though the lung is smallest in size, the alveoli are not fully collapsed due to the surface tension lowering property of the surfactant. Transmural pressure across the chest wall. This is the difference between intrapleural pressure and the pressure around the chest wall. The body surface pressure or barometric pressure. The transmural pressure across the chest wall is usually negative as the intrapleural pressure is negative relative to the atmospheric pressure. Pressure across the respiratory system. This is the sum of the pressures across the lung and across the chest wall. So this is calculated as the difference between alveolar pressure and barometric pressure. Relaxation pressure volume curves. The interaction between these transmural pressure determines the lung volumes and capacities, so which can be studied by analyzing relaxation pressure volume curves of the lung, uh, chest wall, and respiratory system. At functional residual capacity, the transmural pressure across the respiratory system is zero, and at total lung capacity, both lung and chest wall pressures are positive. This indicates that both lung and chest need positive transmural descending pressures. So this is a curve showing relaxation pressure volume of lung, chest wall, and the respiratory system. So this is of chest wall, and this is of lung, and this is of whole respiratory system. The resting volume of chest wall is 60% of the total lung capacity. So this is the volume at which the transmural pressure for the chest wall is zero. This means that at volumes less than 60% of the TLC, the chest wall tends to recoil outward. At volumes more than 60% of TLC, chest wall recoils inward. It should be noted that at transpulmonary pressure 20 centimeter of water, lung reaches its elastic limit. Therefore, the pressure curve flattens beyond this pressure. The increase in the transpulmonary pressure above 20 centimeter of water does not increase the lung volume much, as the distension of the lung is limited by connective tissue of the lung. Further increase in the pressure results in the rupture of alveoli near at the lung surface that can lead to pneumothorax, that is escape of air into the pleural space. So this is all about the different lung volume capacities and the compliance of the lung in brief. Thank you.